Okay, we're going to continue on and roll through chapter 7, and maybe keep rolling. We'll see. Then we will take our exam in a bit during lab. So in chapter 7, we really were talking about types of reactions and ways to really classify reactions. And remember, as we talked about last time, pretty much reactions will, for the most part, break down into two types, big categories. The ones we focused in on last time are double displacement reactions. And in double displacement reactions, the way you know that you have a double displacement reaction is you always will be begin with two ionic compounds. So it's pretty much like I mentioned last time, the only reaction where you are going to start with basically two ionic compounds. And once you see that, you should be able to recognize it as a double displacement reaction. Always with a double displacement reaction, we're just going to basically swap partners here. And on the other side there, we will make two new ionic compounds. And double displacement reactions really account for sort of two of the three reasons why reactions in general take place. And those two reasons are a more specific classification, which is known as a precipitation reaction, which is a type of double displacement reaction. And that's when one of these guys pretty much make a solid. So some type of solid is formed, a precipitate. And that is more specifically called a precipitation reaction, even though it's basically a double displacement reaction that's happening. The other type of thing is more specifically double displacement reactions are called acid and base neutralization reactions. And the result of that is one of these guys here will actually make water, which is kind of the second reason why a reaction takes place. Remember, there's kind of three reasons: is solid being formed, water being formed, and electrons being transferred are the basically three reasons why a reaction takes place. Double displacement reactions basically account for two of those three reasons. We also saw that we can write a molecular equation that shows everything that's going on. If you use something like our solubility rules that we also talked about, something like silver nitrate, because it has nitrates, always going to be soluble. React it with something like sodium chloride, because it has sodium, also going to be soluble in everything. This again is a double displacement reaction where the silver will then go and hook up with the chloride based on solubility rules. That's one of the exceptions for chloride. That's going to make it insoluble, which is why you would get a solid in this case. And our sodium and nitrate will come together and make sodium nitrate, both of which are soluble in everything when we looked at those solubility rules. We could write an equation that really describes sort of what's happening in the beaker or test tube, and that's known as the total ionic equation, where we basically break apart anything that's a strong electrolyte, anything that's a solid, liquid, for the most part gas, and anything that's a weak electrolyte does stay together. So here we would break apart silver nitrate into its ions, as that's basically what's happening. It's floating around in the solution. Same thing here with our sodium chloride, also a strong electrolyte, would break apart into its ions. Here, the silver chloride is a solid, so it's got to stay together, otherwise it would not be a solid. And our sodium nitrate will also break apart into its ions. I'll go underneath here as well. And that's an equation that basically describes sort of what is truly going on in the reaction. And when we look at the total ionic equation, we should be able to find ions on both sides that look identical. So we have nitrate, we also have sodium there on both sides. And those guys that are the same ions on both sides, those are what are referred to, as we talked about, as our spectator ions. And our spectator ions are pretty much like the name implies. They're just hanging out, watching what's going on. They're not directly related to or important in terms of the product being formed in this reaction. So typically speaking, we cross out our spectator ions, and we're left with the third type of equation we talked about, which was the net ionic equation. And that basically is the equation that tells you, for the most part, exactly what is happening in this reaction. And in this particular reaction, what's exactly happening is it is the silver from the silver nitrate that's going to go find the chloride from the sodium chloride, and those two ions are going to come together and make this solid, and that precipitate is basically the main thing that's happening in this reaction. Where are the spectator ions in this case? The spectator ions, if you looked at the beaker, they're still just floating around, basically. And your sodium chloride, which is actually or silver chloride, which is actually a white solid, is basically the guy that's a solid that's be floating around in that, not really floating, it might be floating a little bit in that solution. Any questions on that stuff we talked about? Okay, so we're then going to talk really about sort of the other classification of reactions, which are redox reactions. And redox reactions basically account for the third reason why a reaction takes place, which is basically a transfer of electrons. So pretty much our double displacement reactions take care of solids and water being formed. Our redox reactions, ultimately what is truly happening, even though it may look like different types of reactions, is somewhere along the way there's some electrons being transferred from one substance to the next. So let's get into those. So oxidation and reduction reactions, which are shortened to sometimes be called just redox reactions, again, pretty much account for those electrons being transferred. When we have something that is an oxidation or something that is going through oxidation, it means that it has lost electrons or will lose electrons. And if something goes through reduction, it means that something has gained electrons. Sometimes people remember that Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. People are fond of the oil rig as well. Oxidizing is losing, reducing is gaining. You can put Leo the lion on the oil rig. He goes grr. You don't have to choose. You can use them both if you like. But that is what we can use. So what we want to sort of think about is, how do I know something's being oxidized or reduced? It's a pretty important sort of concept, especially when you're dealing with redox reactions. You want to look at the substance on the left-hand side of the arrow and the same sort of element on the right-hand side of the arrow, and you want to compare what is really known as its oxidation state, or number, which is not necessarily the charge we always assume elements are in an ionic compound. And sometimes they are the charge in the ionic compound, but sometimes they're not when it's covalently bonded. Certain things and certain elements, when we look at them, that we normally think about, for example, as being like -1, like chlorine. When we think about chlorine in a ionic compound, we think of it as having a -1 charge. But if you have chlorine in a covalently bonded situation where it's sharing electrons, it could actually take like a positive charge, like a +7, a +6 type of oxidation state. And that is because it's actually sharing electrons with something that's more electronegative, so it makes it more positive in that situation. In the case of an ionic compound, those electrons are going to be completely transferred, and we get a negative charge on it like we normally assume. So one way you could kind of determine if something's being oxidized or reduced is very simple sort of number line approach. And on a number line, there's 0 usually, and then to the right are positive numbers, to the left are negative numbers, basically. And when somebody loses an electron and goes through oxidation, they become more positive because they have less electrons and more protons. So they become more positive. So if you compare the guy on the left-hand side element to the element on the right-hand side, and their oxidation state becoming more positive or moving in this direction on the number line, that such guy is going through oxidation. Now, when somebody gains electrons and goes through reduction, they become more negative. And that's because they have now gained more electrons. So they have more negative electrons than protons. So they become more negative. So again, if you compare on the left-hand side to the right-hand side the same element, and you look at its oxidation state, and you see it is getting more negative or moving in that direction, that guy is going through reduction. So for example, here we could take a look at something like if I had, let's say I had O2 on this side, and we'll just do like MgO or something like that. And we're just going to look at the oxygen. We have magnesium too here as well. But we'll just look at the oxygen, for example, here. And Oxygen on the left-hand side, that O2 has a zero oxidation state. Remember that that is normally how oxygen comes when it's by itself. Remember that any element that you have on the periodic table that is not combined with anything else, that's just by itself, has no charge. Things only get charges when like metals and nonmetals come together and they make an ionic compound. If you just have like a piece of magnesium, you had a piece of sodium by itself, uncombined, it has no charge. It only gains charges when it basically comes together. On this side, the oxygen does have a -2 charge because now it's hooked up with magnesium, and that's where we have our electrons actually being transferred in this case. So if we look at the oxygen on the left, we could use our number line to determine, what is going on. Oxygen on the left started at 0 and ended on the right-hand side at -2, which means it is moving to the left-hand side, right? And it's becoming more negative. That means oxygen here is being oxidized or reduced. It is being reduced. Yeah, it's becoming more negative. The nice thing about oxidation and reduction reactions is they always occur together, which means if somebody gets oxidized, somebody else has to get reduced, which means if you could just identify one of those things happening, the opposite thing is happening in the other thing that's there. So by default, what we know is the magnesium here is actually being oxidized. Yeah? And we could actually figure that out on the number line as well. If we look at magnesium over here, it has a 0 charge. Again, no oxidation state because it's by itself. When it hooked up with the oxygen, that is when magnesium makes its normal +2 charge. And if we look at magnesium on the number line, magnesium started at 0 and ended on the right-hand side at +2, which means it's moving in the positive direction. And anybody moving in that positive direction is going through oxidation. So you can very simply sort of look at really, it is the oxidation state, or you could call it the charge at this level, is fine. But you could look at the difference in the charge from the left to the right-hand side of those elements, and you can just basically figure out if it's being oxidized or reduced. Question on that, I'll balance it like a real chemistry person here. Yeah, I suppose. Now, you could also use this, for example, yeah. The final answer would be, it would be a question, it'd be a couple, it might be a question like what is being oxidized and what is being reduced. So if you were asked, for example, what is being oxidized, you would say magnesium, and what's being reduced would be the O2 or the oxygen. By the way, what is being oxidized and what is being reduced is always on the reactant side. So that's always found on the reactant side, not the right-hand side of the arrow. So those guys are on there. More importantly, it will help you maybe realize that it's a redox sort of reaction more for our level of what we're going to talk about and that type of stuff. Yeah. Now, you could also use this, for example, let's say I had iron with a +3 on the left-hand side, and it goes to iron with a +2. Is it being oxidized or reduced, this iron? Okay, so we can, again, very easily just kind of use our number line to help us. Obviously, the oxidation state on any ion is the same as its charge, so this would have a +3. On the right-hand side, the iron obviously has a +2. So if we just kind of mark that on our number line, +3 is probably around here, and +2 means we are actually moving in that direction, right? And that means that this guy is actually going through reduction, right? He is being reduced in this case. Any questions on that? Again, becoming more negative. Yeah. Now, when we talk about oxidation and reduction, there's also two other terms that are sometimes used, and that is the oxidizing agent and the reducing agent. Now, these names sometimes confuse people. So if you are being asked, what is the oxidizing agent? That is the substance that is being reduced. And if you are asked, what is the oxidizing agent or reducing agent? That is the substance that's being oxidized. So the oxidizing agent is actually the thing getting reduced, while the reducing agent is actually the thing being oxidized. That is because they cause that effect in the other substance. So for example, if we look at this example of magnesium and oxygen, the oxygen is being oxidized. the magnesium is being oxidized, that means that the magnesium is my reducing agent. It is the reducing agent because when it loses electrons, that allows somebody else to gain electrons and be reduced. So it's causing the reduction in the other substance. Now, when I look at the O2 here, it's being reduced. That would be my oxidizing agent. And the result of that is, in order for it to be reduced, it has to gain electrons. The only way it could gain electrons is it has to cause somebody else to lose electrons. So it causes somebody else to be oxidized. So if you're asked what is the oxidizing agent or the reducing agent, that is a different question than what is being oxidized and what is being reduced. So if you're asked about the agents, it's the opposite of the name is an easy way to remember that. If you're asking what's being oxidized or reduced, it is basically the number line, what's becoming more positive, more negative. Any questions on that there? So in all these type of reactions here that we're going to talk about, these are redox reactions. They basically all involve a transfer of electrons that's going to occur. So let's take a look at these here and a few more examples. So if we look at this reaction here, sodium metal by itself, once again, has no oxidation state. Chlorine here by itself, how it naturally comes, has no oxidation state. It's zero. When those two guys come together and make an ionic compound, that is when they gain really oxidation states of +1 and -1. So once again, if we take a look at our number line here and we look at the sodium, sodium on the left-hand side started at 0. On the right-hand side ended at +1, which means it's moving in the positive direction. That means that the sodium here is being oxidized, yeah? If we look at the chlorine, chlorine started at 0, ended on the right-hand side at -1, which is moving in that direction on the number line, becoming more negative. The chlorine is being reduced. Which one here would be my oxidizing agent? It would be the chlorine, the opposite of the name, basically, right? And the reducing agent would be the sodium. So this reaction of making an ionic compound here is a redox reaction. What is ultimately happening is that sodium is transferring its electrons over to chlorine. And we got a transfer of electrons, which is why this reaction takes place. By the way, a really easy way to know what is being oxidized, what is being reduced. When you always have a metal, right, and a non-metal, which one should always be oxidized? Which one should always lose electrons? Metals, right? Because they become positively charged, right? Cations. And nonmetals become negatively charged, which means they should always be the ones that get reduced when you have a metal and a nonmetal. That's basically what happens in an ionic compound. The metal sends the electrons over to the nonmetal. Any questions on that there? So again, as I mentioned, this is what is referred to as a redox reaction, which is, again, the big umbrella of types of reactions. There's our magnesium example there that we just talked about, which is also obviously a redox reaction happening. We could write what are referred to as half reactions. These are what are referred to as half reactions. One is a oxidation half reaction. And in an oxidation half reaction, the electrons are found on the product side, indicating that they're being lost or given off, basically. And this guy down here is the reduction half reaction. And in that case, we will see the electrons actually on the reactant side, like they are being gained or accepted. They are called half reactions because, frankly, if you add those reactions back together, you get the overall reaction that's taking place. So if you were to add both of these reactions back together and you balance them correctly, you would get back the overall reaction. The electrons will always cancel out. You can think of the arrows like an equal sign. So anything on opposite sides of the arrows will cancel out or reduce. The electrons should always cancel out because whatever number of electrons somebody loses is the exact same number of electrons somebody gains. So there's always that kind of perfect transfer of electrons from one side to the next. And if we balance it like here with our 4 electrons, once again, our electrons will cancel and we'll be left. Everybody on the left-hand side stays on the left-hand side. Everybody on the right-hand side of the arrow, these two ions will come together to make the ionic compound that's on this side, basically. There are 4 electrons in this equation because there are 2 magnesiums, right? And each magnesium will lose 2 electrons. So grand total of 4 electrons getting lost, 2 from each magnesium that's going to lose electrons. All right, we're not going to worry too much about that. There are some other definitions of oxidation and reduction. All right, so let's talk about classifying reactions. Some of these we talked about previously. As I mentioned before, these are the 3 reasons why a reaction takes place: formation of a solid, formation of water, and a transfer of electrons. So last time we talked about precipitation reactions, which again are double displacement reactions. Positive, negative, positive, negative. Again, going to switch partners here. The result of that in this case is we get this solid that is formed, and that is what is basically referred to as a precipitate, and why this is a precipitation reaction. This reaction again falls under the double displacement umbrella. It is not a redox reaction. There is no change in oxidation states from left to right. If you look at the potassium on the left, it's +1. Potassium on the right is +1. The chromate on the left is -2. Chromate on the right is -2. Nitrate -1 on both sides. There is no change. There's no electrons being transferred in this type of reaction. This is again accounting for basically our solid being formed. Bless you. So as we talked about, again, we got that double exchange. And as we also talked about last time, we want to always make sure if we are predicting this side, we get the proper equations down and formulas down first before we go into the whole balancing aspect of it. The other type of double displacement reaction that we talked about last time is an acid-base reaction. Again, this being our acid, this being our base, still a double displacement reaction happening here. This, again, just like our precipitation reaction, does not involve any electrons being transferred. So there's no electrons being transferred here. The result of this one, as we talked about, is the formation of water. So again, acid-base neutralization reactions and precipitation reactions are 2 more specific classifications of double displacement reactions, where again, our positive guys switch partners, basically, in this case. Remember that, as we also talked about last time, you can take any combination of strong acid and strong base, and you will always hit water, basically, is the ultimate reaction that's happening. If you go all the way down to the net ionic equation, that is essentially what is taking place. All right, so now here we're getting into some redox reactions here. And in our redox reactions here, we have a more specific classification of a redox reaction. Again, this is going to be a single replacement reaction. The top one up here is not a single replacement reaction. This is still a redox. These are both 0. That is +1, -1. So again, if you look at what is happening, lithium starts at 0, ends at +1, becoming oxidized. Fluorine is starting at 0, ending at -1, becoming reduced. And again, this is a redox reaction happening. So right here is our single replacement reactions. If you remember, we saw single replacement reactions, a number of test tubes that you did when you had to put your finger on it and light the splint and pop the sound there, the barking guy when you put the piece of magnesium and hydrochloric acid. Also, we did it with the halogens as well. So single replacement reactions have this general formula: A plus B, C. This is an ionic compound. And if this is a metal, the metal will come in and kick out the positive guy and make a new ionic compound, and that guy will come out basically with no charge, and the metal has no charge. If this is a non-metal, he will come and kick out the negative guy and make a new ionic compound and no charge. Remember, for this reaction to take place, whatever is coming in needs to be more reactive than what it is replacing. So A in this case would have to be more reactive than B for this reaction to take place. A would have to be more reactive than C for that reaction to take place, or the reaction will not take place in that case. So that's what we see here. Zinc has no charge. That's +1. That's -1. That's no charge on the hydrogen on the right. +2, -1. The zinc will come in and kick out the hydrogen. When it does, it makes that hydrogen gas that you keep lighting the splint to spark and all that kind of stuff, the bubbles. The zinc and the chloride come together in this reaction. That is your classic single replacement reaction. It is also still a redox reaction happening. Again, if you look at what is happening in this case, our zinc on the left starts at 0. Our zinc on the right becomes +2. It is being oxidized. It is the hydrogen here on the left that starts at +1, ends at 0. It is actually being reduced. What's happening with the chlorine? Anything? Charge on the left is -1. Charge on the right is -1. Nothing's happening with it. It is still the same. It is a spectator ion, just like we had when we did double displacement reactions. The chlorine is just floating around. There's nothing really happening here. What is ultimately happening here, if you get to the net ionic equation, is zinc plus that H plus. It's going to make H2 plus zinc. The zinc's going to send over 2 electrons there to the hydrogens. And that's what's happening here, is that transfer of electrons is ultimately what's happening. The chloride, like I said, is basically just, still floating around as a spectator ion. It's really not doing anything here. So a single replacement reaction is a more specific classification of a redox reaction that's happening, basically. Yeah. All right. Another type of reaction is a combustion reaction. And in a organic combustion reaction, this is an organic compound that usually contains carbon, hydrogen, oxygen. The classic markings of an organic combustion is you have O2 on the left, always make CO2 and water. This is like when I took the Bunsen burner carefully and heated the bench top, right? We saw the water being formed. That was a combustion reaction, basically, that took place. So a combustion reaction is also still a redox reaction. So it still falls under the umbrella of a redox reaction that is taking place. And when we look at a combustion reaction, there's also a more general definition of combustion. Pretty much, that is all you need. On the left-hand side of the arrow is O2, and you could classify it as a combustion reaction. So a really super basic definition of, I want to call this a combustion reaction, is you can basically just need O2 on the left-hand side, and that's it. Most of the time, I would say 9 times out of 10, or even more than that, if somebody's talking about a combustion reaction, they most likely are talking about the organic combustion reaction, where you have the organic guy plus the O2 makes the CO2 and water. I would say most of the time, these are the type of combustion reactions most people talk about. Again, we have an organic guy, oxygen, CO2, and water. So that, I would say, most of the time is probably the combustion reaction you're going to see. But really, all you need for a combustion reaction is O2 being present on the left-hand side of the arrow. And technically speaking, it could be a combustion reaction. Now, another type of reaction, like we saw when we were doing the lab the other day, is a combination or synthesis reaction. This is also still a redox reaction. And in this case, basically, it has this general formula. 2 things make 1 thing. So 2 things make 1 thing. Two things make one thing, basically. These are synthesis and combination reactions. These are also still redox reactions. So if you take a look at the sodium here, 0, right? The chlorine, 0, +1, -1, like we looked at earlier. Again, the sodium starting at 0, ending at -1, becoming more positive, being oxidized. The chlorine starting at 0, becoming -1 on the other side, becoming reduced. So although it can be more specifically classified as a synthesis or combination reaction, ultimately what's still happening here is a redox reaction. There's still electrons being transferred. I will say that most of the time people would probably classify this as a synthesis or combination rather than just a redox reaction. So a lot of times people take the more specific classifications, but you could absolutely classify it as a redox reaction. This also brings up a good point if we take a look at that equation we saw earlier with the magnesium. We were able to classify this as a redox reaction, right? Because there's electrons being transferred. It also could be classified technically as a combustion reaction because there's oxygen. And that is two things that make one thing, which means you could classify this as a synthesis or combination reaction. So this one reaction could actually be classified three different ways depending on what you're looking at. This is a redox reaction, there's oxygen, so it's a combustion reaction, and there's two things making one thing, which means it's a synthesis or combination reaction. So you can classify a reaction multiple ways depending on sort of what you're looking for. You should choose the best way. I would say most people would roll with synthesis for this reaction or combination, but it can be classified in any of those ways. Technically, all those things are happening. Any questions on that there? So synthesis, two things make one thing. That should be synthesis with an N. All right. The kind of direct opposite of that is a decomposition reaction. In a decomposition reaction, you take one thing and you break it apart into two or more things. So it's like the complete opposite of putting it together with synthesis. You're going to break it apart. This is also a redox reaction. This is what was done when we did the electrolysis of water, right, with the 9-volt battery, and we held the hydrogen gas and oxygen gas being made. That is one thing makes two things. By the way, this is still a redox reaction as well. And we can see that if we actually look at what's happening here. Hydrogen is +1, oxygen is -2, and these guys are 0 on that side as they're in their natural state. That means hydrogen is starting at +1 and ending at 0, which means the hydrogen here is being reduced. The oxygen is starting at -2 and ending at 0 on the right-hand side. It is the oxygen here that is being oxidized in this case. So it is still a redox reaction, but it is more specifically classified as a decomposition reaction. Question on that there. So to summarize what we talked about here, we have two big categories of reactions: double displacement, and again, and that is going to account for our solid being formed. It's going to account for water being formed. Underneath that umbrella, more specific classification is a precipitation reaction and our acid-base reaction, where that accounts for that and that accounts for that. The other big category is our redox reactions, which basically account for our electrons being transferred. And underneath there, we have a synthesis reaction is a more specific classification. Our combination reaction is sometimes called. We have a decomposition reaction. We have a single replacement reaction. and we have a combustion reaction. So again, we have these big sort of categories of reactions and more specific ways to classify it. And all these reactions, even though they all have different names, it still involves basically electrons being transferred in every single case. Any questions on how to classify reactions there? All right, that wraps up chapter 7. We're going to go to chapter 9 next here and kind of put together everything that we've been talking about. All right, so let's take a look here. Okay, so in chapter 9, we're going to actually put together several things we've been talking about. We're going to put together our balanced equations. We're going to put together our grams to moles. And we're going to do basically calculations from a balanced equation. So this is very much like the experiment we did last week, 15. And we're going to do some stoichiometry type calculations. So important in this sort of idea is how we look at a balanced equation. And when we look at a balanced equation, we can look at the coefficients, which are, again, our numbers that come in front. And we could use these to find relationships from the equation. We could say, for example, 2 molecules of H2 react with 1 molecule of O2 to produce 2 molecules of H2O. By the way, those numbers are nothing more than the coefficients. So nothing, no mystery here, just the coefficients from the balanced equation. The relationship that we're going to use in this chapter pretty much exclusively is this relationship here, which is sometimes referred to as the mole-to-mole relationship. And it also is just the coefficients. So we could say that 2 moles from the coefficient of H2 react with 1 mole of O2 to produce 2 moles of H2O. That is a relationship that we could use to do calculations from the equation using what is known as stoichiometry. The last relationship down here is the law of conservation of mass, which means if we started with 2 hydrogens on the left, since each hydrogen is 1 gram, that's about 2 grams on the left-hand side of the arrow, and we should still have 2 hydrogens on the right-hand side of the arrow, which is about 2 grams. So the molar mass of everybody on the left-hand side and the right-hand side should be the same as we have that conservation of our elements. So let's talk a little about stoichiometry, which is a calculation that's a really important calculation in chemistry. It is also a calculation that people freak out about because they think it's got to be harder than it is. And if you don't overcomplicate it, it is not that difficult of an idea to sort of get. The idea of what stoichiometry is pretty much just a conversion factor. And it's a conversion factor that we don't look up in a table, but we actually get from the equation. And that is the reason why we do that, for example, is if we had a reaction, and let's just say we only knew like how many grams of this guy we started with. But we wanted to know, for example, how many grams of this guy would we produce? Right? That is something that stoichiometry calculation will allow you to sort of figure out. You could also figure out, by the way, if you knew how many grams of this guy, how many grams of the other reactant you would need as well. So you could use stoichiometry to figure out how much reactants you would need. You could do stoichiometry to figure out how much products you should make. You could also do stoichiometry going the other way. If you know how much you produced, you could back calculate and figure out how much reactants you had to start with to produce that much. So we could do stoichiometry across the arrow. We could stay on the same side of the arrow. We could go to the right-hand side, left-hand side of the arrow, and we could do these relationships. So the units of stoichiometry, as we will see in some different chapters as we go through, will be a lot of different units. Could be moles, it could be grams, it could be liters. I would say in most cases in this chapter, we're going to be doing this really important conversion, which is grams to moles and moles back to grams. So hopefully you remember that it is the molar mass from the periodic table that allows you to do that. Remember, the molar mass comes from the periodic table. It is the number on the bottom. That is how many grams there are per mole. You could use that as a conversion factor. You could flip it around and put the moles on top and the grams on the bottom. If you have a molecule, right, you just go to periodic table and add up all the parts. So there would be 2 times 1.008 grams per mole for my hydrogens. I would add that to 16 grams per mole for my oxygens, and that would give me a molar mass for water of 18.02 grams per mole. Once again, you can use that as a conversion factor, 18.02 grams per mole, or you could flip it around. A mole is 18.02 grams. So that in stoichiometry problems is a calculation we use a lot. We use it like at the beginning of the problem a lot of times, and we use it at the end of the problem. So we use it, that kind of conversion factor, molar mass, a lot from the periodic table. So that is a very common one. Avogadro's number, not so much. So usually this is basically going to be a lot of times molar mass and grams to moles. All right, so these are the basic steps for stoichiometry problems or basic stoichiometry problems. And what you want to do is you want to write the correct formulas for the reactants and products, and you want to make sure that you have the right formulas and you have the balanced equation. I would say most of the time you will be starting probably at step number 2, which is you want to make sure that you have a balanced equation. So really that is in most cases your first step. Stoichiometry problems will not work correctly if the equation is not balanced. So no matter what you do, if you're not given the equation but given everything in words, you want to make sure you get the right equation down and then balance it. If you're given the equation, you want to double check to make sure it's balanced before you start the calculation. Otherwise, you're not going to do the calculation correctly. The next thing that you typically want to do is take whatever they give you, and you want to take what they give you and get it to grams, and then go from grams to moles using the molar mass. So in a basic stoichiometry problem, they could give you some type of information in any unit that could be out there. You basically want to get that unit to grams and then go from grams to moles using the molar mass from the periodic table to do so. Step number 3, really, which is step number 4, I think, on here. This is actually the big stoichiometry part. You want to go to the equation and find the mole to mole relationship between the two things you're interested in. And that would be from the balanced equation. The two things you're interested in is a very simple thing to determine. The first thing you're interested in is whatever they gave you. So they gave you a number that went with something. So whatever that thing is one of the things in the equation you're interested in. The second thing that you're interested in is whatever you're trying to find. So whatever you're trying to find for the answer, that is the other thing in the equation that you're interested in. You would go to the equation. You would find the coefficients for those two, and that would give you the mole-to-mole relationship, and that's what you would use for your balanced equation there to do the conversion factor. The last step, which is step number 5 here, is you're going to use the moles, and you should be in moles at this case, and you're going to convert it into some other unit. And that usually will result in moles going to grams using the molar mass, again on the back end. And it can be really any type of unit that you want. But most commonly, you're going to use your grams or your moles and convert it back to grams. Okay, so again, that 4th step, you're going to go moles to some other unit, and most likely it's going to be grams at the end, and you're going to use that molar mass. So these are the 4 basic steps for a stoichiometry problem, and you should always basically follow those steps in order. And if something is done for you, you should just continue to the next step. If something is done for you, don't undo it and redo it. Sometimes people do crazy things like that, like it's already in moles, so I want to unconvert it from moles and then convert it back to moles and stuff like that. So just continue down those steps. So let's talk about how we get these relationships. So if we have a balanced equation like this one right here, from this one balanced equation, we could come up with a number of conversion factors that we could use in a particular problem. So we could say that looking at just the coefficients here, and obviously if there's nothing written here, it is a 1, right? We could say that for every 2 moles of CO, I need to put in there 1 mole of O2. And again, that is nothing more than just the coefficients. I could also say for every 2 moles of CO, I can get out 2 moles of CO2. Now I could also say for every 1 mole of O2 I pop in there, I get out 2 moles of CO2. These are all what are referred to as being equivalent to each other. These are equalities. These are stoichiometrically equivalent to each other. They are not obviously equal to each other, as 2 does not equal 1, right? So obviously 2 doesn't equal 1. But they are equal to each other in terms of proportion of what you need to put in there to get this reaction to occur. Like if you're making cookies, right? You need so much flour, so much butter, so much chocolate chips, right? To get a dozen cookies. Same idea here. These are sort of the proportions of each of these things that you got to throw in there together to get that reaction basically to go forward. Now, these are really equalities, just like any other equality we talked about earlier on. For every equality that you have, you basically could have 2 conversion factors that you could write. And we could write 2 conversion factors for each of these equalities. And we could say, for example, for 2 moles of CO over 1 mole of O2, are 1 mole of O2 over 2 moles of CO. And that would be the 2 conversion factors we could get from that guy. From this guy, we could write 2 moles of CO over 2 moles of CO2, or we could flip it around, 2 moles of CO2 over 2 moles of CO. Lastly, we can write for this guy 1 mole of O2 over 2 moles of CO2 are 2 moles of CO2 over 1 mole of O2. From this one equation, this one balanced equation, we got a total of 6 conversion factors that we could use. Will we use all 6 of them? Absolutely not. If you're using all 6 of them, you're doing something really wrong. Yeah. So you're just going to pick one. One out of the 6 is basically all you're going to use, the one that you need. But these are all the 6 that are technically available to us. This is basically what stoichiometry is. It's a conversion. And again, like I said before, instead of going to a table to figure out 12 inches of the foot, you go to the equation to basically get your conversion factor from. Now, how do we use these to put these together here to show you sort of what might we want to do? Let's just say, for example, that in this case, we produced, I don't know, we'll go as 25 grams of CO2. And we wanted to know how many grams of O2 did we start with. So this is a typical stoichiometry type problem. So remember that there are 4 basic steps that we want to follow. The first step is to balance the equation. And in this particular case, that is already done for us, obviously, right? So step number 2 is we want to take whatever they gave us, which in this case, the only thing that they gave us was 25 grams of CO2. And we want to convert that into moles, in this case, of CO2. So that is the second step that you want to do. Take whatever they gave you. Doesn't matter if it's on the left-hand side of the arrow. Doesn't matter if it's on the right-hand side of the arrow. Doesn't matter what unit it is in. If it's in some other unit besides grams, you need to get it to grams and then convert them to moles. So if you had pounds, for example, you would need to take the pounds to grams, grams to moles. So whatever the unit may be, it doesn't matter. In order to do grams to moles, that is where I go to the molar mass to do that from the periodic table. And from the periodic table, if I look at carbon, it says 12.01 underneath it. And if I look at oxygen, it says 16, and there are 2 of them here. So 2 times 16. That is going to give me 44.01 grams per mole. That is the molar mass of CO2. That is my conversion factor that I use to go from grams to moles. That is the molar mass. So that is what I'm going to do in my next step here. I'm going to take the 25 grams that they gave me, of CO2. And I'm going to use the molar mass as a conversion factor. I do want grams on the bottom so they cancel. I want moles up on top. The grams will cancel here. And if I do that and I get an answer, which, by the way, you don't necessarily have to get an answer, but I'm going to do it in each step so you can see the steps here. We will get something like 0.56805, and these are moles of CO2 in this case. Now, I'm not going to round too much because I'm going to continue on with my calculation here. Now, that is the second step. The third step, and really why you have to do the second step, is this is the stoichiometry part of the problem. We're going to go from what we don't want to what we do want. So we know that we were given CO2, right? But we don't want to end up at CO2. We want to figure out the grams of O2, right? So this is where we're going to look and do our mole to mole relationship. And based on this reaction, we already have it up there, so I won't write it again up on top, but I'll highlight it. That is this relationship right there. Yeah. So that relationship right there means that for every 1 mole of O2 I put in there, I should get out 2 moles of CO2. That gave me these 2 conversion factors possible to use in this problem. Now remember that I want to get rid of CO2 and end up at O2. Which conversion factor should I use? The one on the left or the one on the right in this case? Which one will get rid of CO2? Opposites cancel, right? So this guy here will be the one that will get rid of the CO2. So I would take my number from above, my 0.56805 moles of CO2. I will use my conversion factor, which comes from the equation. 1 mole of O2 on top, 2 moles of CO2 on the bottom. This is the big stoichiometry move right there. I'm going to divide by 2, basically. And that's going to give me 0.28403 moles of O2. So that was the stoichiometry part. I basically used the mole-to-mole relationship. And as you can see in this particular problem, I just used one of the 6, right? I didn't need to use them all. Just the one that I needed is the one that I used. Is this the answer I'm looking for, though? This is not the answer I'm looking for because this is only moles of O2. I want grams of O2, which means I need to do the 4th step. And if you do the 3rd step correctly, you should always be in moles. And I now need to go from moles back to grams. We also need to remember that we are no longer at CO2, right? We are now at O2, which means when I do the 4th step here, are my moles back to grams, I need to actually go back to the periodic table and get the molar mass of O2. I can't use CO2 anymore, right? So if I go to the periodic table, I see oxygen is 16, so 2 times 16 gives me the molar mass of oxygen of 32 grams per mole. I'm going to use that as a conversion factor here. So I'll take my number I left off with, 0.28403 moles of O2. We'll use our 32 grams up on top per mole of O2. And that will get me here times a 32. At this point, I can clean it up to write sig figs, which is probably based off of that number, which is about 9.09 grams of O2 in this case. basic stoichiometry problems like this, where pretty much they just give you one piece of information in the equation. How many grams of somebody, how many moles of somebody, how many pounds of somebody, always follows these same 4 steps. Equation balanced, convert whatever they give you to moles, go to the equation, do the mole to mole relationship, and at the end, convert those moles to some other unit. What this means is this number is if I produce 25 grams of CO2, I would have had to put in there 9.09 grams of O2 to produce that much CO2 that I produced to start with. Question on any part of that? By the way, if you wanted to do all these steps and combo them together, you absolutely could. You could go from here to here to here without getting an answer in between. And that's perfectly fine as well. If you do get an answer like I did, I would not round to the very end. And usually in these type of problems, whatever the significant figures are for the original number, that's probably what the answer should be in terms of sig figs. Question on those 4 steps or stoichiometry or that type of thing there. I was taking a look at one here to finish. It's pretty much what we just talked about, so I'm just going to scroll it through. So why don't you try this one? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed when you react 5.32 moles of lithium? So take a shot at there and see what you come up with. Again, follow the 4 steps. We want a balanced equation, probably not with the highlighter. I don't want it, probably. Try that again. Right, with something you can see. We want a balanced equation. We want to convert to moles. We want the mole to mole relationship. And then we want moles to some other unit if necessary. All right, let's take a few moments there, see what you come up with here. Okay, so let's take a look, see how we're doing. We're getting to the end here. So in this case, we don't really have the equation, but we always need an equation if you're doing any type of stoichiometry. But we do have words, so this would be good practice for an hour here. Lithium metal should be just Li, right? Reacts with water, which we know hopefully is H2O. To form hydrogen gas, right? And remember that hydrogen gas is a diatomic, so it's H2, not just H. And lithium hydroxide, lithium's +1, hydroxide is OH minus. So a little lithium hydroxide, right? So now that we have the proper formulas down, we want to make sure that we do balance it. And in this case, I don't know, maybe like a 2 there, like a 2 there, maybe like a 2 there. I feel like I'm just putting 2s. I think that's all the 2s I need, I think. So I got 2 lithiums on each side. I got 4 hydrogens, I think, on each side and 2 oxygens on each side. So we should be good. That should then be balanced. Yeah. Any questions on that? Now, if we read the problem here, we want to know how many moles of H2 we're going to produce. If we start with 5.32 moles of lithium. So the second step is to take whatever they gave us, which was lithium, and convert it to moles. I do not need to do that in this case because it's already done for me. So again, don't undo it. Obviously, if I were given grams, I would have to go to the periodic table and do the molar mass to convert it to moles. But again, it was already done for me. So I'm just going to go forward, don't go backwards, right? So step number 2 is done. That brings us to step number 3. That is the big stoichiometry move. And here we're going to go to the equation and find the 2 things we're interested in. And one thing should be the lithium, since that's what they gave us. The other thing is what we're trying to find, which is this guy. And from that equation, we could come up with our third step here that we need to do. We see that every 2 moles of lithium you put in there, which again is just a coefficient, will give me 1 mole of hydrogen, which is also the coefficient there for hydrogen. That again will give me 2 conversion factors that I could use. Again, I'm not going to use them both. I'm going to use whichever one is going to work for me in this case. And what one I need to use will be determined by what they gave me, which was 5.32 moles of lithium. In this case, I want to get rid of lithium, so we need to go opposite location for lithium, which means it needs to go on the bottom there. So it is going to be the conversion factor here on the right that's going to work, and that is the stoichiometry move. If you blink, you might miss it. It is just a conversion factor here. And our moles of lithium are going to cancel, so we're essentially going to take 5.32 divided by 2. That will give me 2.66 moles of hydrogen. I am looking for moles of hydrogen, which means that is my answer, right? I only had to go to step number 3. I did not need to do step number 4 in this case, right? Any questions on that? That right there is basically saying that if I started with 5.32 moles of lithium in this case, everything went perfect. No bad side reactions. I should theoretically get out 2.66 moles of hydrogen. That is also known as the theoretical yield, which is what you get when you calculate it from the equation. We didn't need to do it in this case, but if I wanted grams, just to show you, again, not needed here. But if I wanted grams, I would do the 4th step, which means I would take my moles. I would have to go to the periodic table, get my molar mass of hydrogen H2, which would give me 2.016 grams per mole. And I could figure out how many grams that would represent, 2.66 moles of H2, using the molar mass from the periodic table, 2.016 grams per mole. Moles of H2 will cancel. And in this case, that would be something roughly like 5.36 grams of H2. That would be the theoretical yield in grams. Yeah. So that would be the theoretical yield in grams, which is very common what we usually calculate because, as you know, right, when you go weigh something, it's grams usually that we look at. And so a lot of times we want to know how many grams we would produce when we weigh something out, is how many grams we need to put in there. And that would be the theoretical yield there in grams. And again, this comes from the periodic table, obviously, the number on the bottom there for hydrogen. Once again, the same 4 steps: balanced equation, convert to moles, ready, done for us, mole to mole relationship, and not needed, but did it for free. Convert those moles to some other unit. Basic stoichiometry problems like we did in experiment 15, pre-lab, post-lab questions are basically these type of steps. Just follow those 4 steps. In the case of experiment 15, you know how many grams you weighed out of the Ki, and that should tell you how many grams of the lead 2 iodide you should produce by following these same 4 steps, and that's how you would get to the theoretical yield. Any questions on that there? All right, we're laid up there for